looking at sapling later ones. This is number 28 from chapter 6. This is showing this alkene. And it's going to react with Br2. So, and they're asking, right, is this alkene E or Z? First we've got to answer that question. Is this alkene E or Z? And how do we decide if something's E or Z? So well, how do we decide it though? We split it in half, right? We split it in half. And we say, okay, first of all, this is a hydrogen here, right? That's one of our rules. Draw on all the hydrogens on the alkenes. So hydrogen versus carbon, who wins? Carbon. Carbon versus carbon, who wins? Tied. Carbon can't beat carbon. This one's bonded to a carbon and 2 H's, and this is bonded to 3 H's. High card wins, so who wins? This one, right? So it's a Z alkene. Right, Z same side. Right, so we all agree on that. Good. Now let's think a little bit deeper about this. So we've seen the mechanism for this. Mechanism shouldn't be an issue. Now we're going to think about the stereochemistry. This is the next level, right? This is where we can take chapter 4, the R and S stuff, and combine that with these reactions we know. So, what's the hybridization state of these? Oh, we should follow our rules. What other rules do we have? Oh, okay, good. 1, 2, 3, 4, 5, 6. What are the other rules we have? Draw on the number of the carbons. Draw on all the lone pairs. Where should I draw lone pairs? On the bromine. How many lone pairs does bromine have? 3 lone pairs, yeah. Okay, good. Step 1 is done. Step 2 is bonds broken, bonds formed. Can that work here? Sadly, no. We don't know the product, so it can't work here. So we got to skip that one. What's the next rule? Identify the nucleophile and electrophile for each step. All right? And where do we start our arrows at? On the nucleophile. Which one? And what's the nucleophile in this case? The pi bond first is. The pi bond first is. Right? That attacks the bromine. That breaks this bromine-bromine bond. And then these bromine electrons come back down and attack. And we make a bromonium ion. When we balance our charge, there should be a Br minus, right? That's the last thing we always do. We always check to make sure we balance our charge. Overall, we had no charge in the beginning. Overall, the next step, we better have no charge as well, right? Cool? So what does this have to do with stereochemistry? Well, let me show you. Shrink that down a little bit. You can still see that. This pi bond, that carbon 3 and carbon 2, what's the hybridization state of carbon 3 and carbon 2? sp2, meaning it's what shape? What geometry does it have? Trigonal planar. Right. So one way we can think about this is there's 2 p orbitals here, right? This is carbon 2 and this is carbon 3. And there's electrons in these orbitals, right? Does the shading, does that mean that's where the electrons are at, right? The shading? No. No. It's just shading. The electrons are both there. So what else is going on here? Well, on carbon 2, it looks like we have a carbon 1 is coming out at us, right? And that alkene, and that H would be wedged going away from us, right? What else would be in this? Would also be wedged on? What's wedged on carbon 3 then? The methyl or the ethyl? The ethyl. See how remember we just got done doing E and Z, right? The methyl and the ethyl are on the same side. So if this is wedged, that means the ethyl must be wedged. And then what's going away? The methyl. So let's number our carbons. 4, 5, and 6. Cool. Okay, so what does this matter? Do you think, right, we talked about carbocations, right? If I have a carbocation and the p orbital is empty, Does a nucleophile have any preference whether it attacks this way or this way? Does it care? No, why not? What? Why can't it attack both? That's right. Why can't it attack both? Why is there no preference? Is this lobe any less without electrons than this lobe? No. Is this top part of this pi bond any more filled with electrons than this bottom part? No. So, the bromine can either be on the top or the bottom. If it comes like this, let's say the bromine comes from the top. So these electrons in this bond, right, attack. These come back down. These kick off the Br. What would that give? That would make the bromonium ion up, right? So I don't need to change any of my wedges and hatches, right? This can all stay the same. Number my carbons. 1, 2, 3, 4, 5, 6. And the bromine here is now on the top. And we still have Br minus. Right? So that's one face of the alkene. Could the bromine have also come from the bottom side? Would that have given something different than this bromonium ion? What bromonium ion would it have made? What's the relationship between this bromonium ion and, if I shrink it up again, what would the other bromonium ion look like? It would look like the wedges and hatches don't change. Right? Because if an alkene's E or Z, that's a thing. That stays that way. 1, 2, 3, 4, 5, 6. Except now the bromonium ion's down here. What's the relationship between this bromonium ion and this bromonium ion? What are they to each other? They're stereoisomers. What kind of stereoisomers are they to each other? They're enantiomers. They're mirror images of each other. Right? They're exactly opposite in every way. One is on the top, one is on the bottom. Right? Just like in a carbocation attack, when you attack a carbocation, you could attack from the top, get the wedge, or attack from the bottom, get the hash, right? You could get R, or you could get S. Right? There's no preference. So you get a mixture of enantiomers here. We see that? So the second part of this mechanism, which we know, right, involves Br minus. Now, which carbon is Br minus most likely to attack? Carbon 1, 2, or 2 or 3, I guess, right? Which one? Which one's the most likely to attack? 3. Why 3? So it has more hyperconjugation, right? The fact that it's more substituted is not the reason why. The reason why is because it's more substituted, it has more hyperconjugation, which makes this carbon more delta plus. Now, another thing to notice, we always get trans products. So the product of this, if I move this stuff over here, let me show you. I'll show you what the product is beforehand. The product with this enantiomer, this is what you get. You get the bromine. Number our carbons, 1, 2, 3, 4, 5, 6. And the other bromine is this way. Do we see how our bromines are trans? Do we see that? Right? It's almost like this is on the top part of the, if this was a ring, right? This would be like the top of the ring, this would be the bottom of the ring. So the bromines are trans. Why are they trans always? They're always going to be, not because it's more stable. Nope. So it's not because of stability. Remember sigma star? Who remembers what happens? What happens if you put electrons in an antibonding orbital? What do you do to a bonding orbital? Yin and yang. Remember doing bond order in Gen Chem?
Does it lower the energy level?
No, it doesn't lower the energy level. Right, so remember you guys did these things where there'd be like this. There'd be two levels and there'd be like a sigma and then a sigma star. And you'd say, okay, if I have 3 electrons, that decreases the bond order. Right, if I had this, I have a bond order of 0. Right, remember doing that? Anybody? You did. Okay, fine. It's fine. We'll take it from a different angle then. Where are the electrons? So we're all convinced. We know we're going to carbon 3, right? We know we're going to carbon 3. And we know we're going trans. Now we got to explain why is it trans. So where are the electrons in the bonding orbital? Where are most of the electrons at? Are they on the bromine or the carbon?
The electrons?
And this bond right here. There's 2 electrons in this bond. Who's hogging them? Bromine or carbon? Bromine. Why? But there's more electronegative. What? But there's a plus charge on bromine. It lied. It's lying. It's lying Lewis dot structure. Right? So most of the electrons are hanging out here in the bonding orbital. Where are electrons not at? And by the carbon. Right? So it's if these are where so the antibonding orbital is 180 degrees away. It's like the mirror image of the bonding orbital. Right? So if you think about here's a carbon bromine bond. Right? Most of the electrons, right, in the bonding orbital are all by the bromine. Right? This is the blue is the sigma bond. Where the electrons are not at is in the antibonding orbital, which is closer to the carbon, because that's where electrons are not at. And that's sigma star. Well, we know where sigma star is at. What's this bond angle from here to here? What's this look like to you? 180. So, where's the Br minus have to attack if it's going to break this sigma bond? It has to attack sigma star. Think about it. If you want to break a bond, what must you do to that bond? Put electrons in its antibonding orbital. What? If you want to break a bond, in all cases, you put electrons in an antibonding orbital. If I have a bond and you put electrons in my antibonding orbital, you break my bond.
So like the opposite, the bonding, the antibond, they're on like the opposite side?
Yes, they're 180 degrees. Well, think about it, right? This is the electrophile, right? Where is this most delta plus at? That carbon. This is showing you where it's delta plus. This is saying, yes, this is where we are delta plus. On this back side. You must attack me from the back side. Right? This is my empty antibonding orbital. Put electrons in there. Right? Think about look at the arrows, how we do it. Right? As the electrons go in there, what happens? These electrons, the bond breaks. Right? You've been drawing the mechanism already, thinking like that. Now we're just putting a name to exactly where that's at. I'm telling you exactly where the antibonding orbital is at now. It's exactly 180 degrees away. So what kind of products do you end up making? They have to be trans. Right? They must be trans. Because the bromine can't come here because that's electron rich, right? There's electrons here. I need to go for the opposite side where there's no electrons, where it's delta plus.
So would that make that carbon the electrophile?
This carbon's still the electrophile, absolutely. This carbon is the electrophile. And now we're just saying exactly where it's delta plus. Right on this, we're saying it's really not anywhere near the bromine. It's in the opposite side of the bromine. That we're just telling you exactly where it's delta plus. Right? There's a lot of math that goes into that, right? But we're just saying this is where it's delta plus.
That's where it needs electrons.
That's where it needs electrons. And if you put electrons in there, you break that bond. If you put electrons in anybody's antibonding orbital, you break its bond. And in this case, because we know where this is at, it has to be a trans product. Now, let's be honest. Chemists saw it was trans, realized it couldn't go through a carbocation, and said, whoa, we got to figure this out. Right? Because if this had gone through a carbocation, would you only get trans? No, because with a carbocation, what happens? You could also you could end up with a cis product. So when they saw this product, they looked at it and said, well, this couldn't have come from a carbocation. This has to be a different mechanism. So overall, layered. You had to do EZ, chapter 4 stuff. You had to do chapter 5, basically basic mechanism type stuff. We added in the fact that a pi bond is planar. So the bromine could have came from the top or be on the bottom. So you get 2 bromonium ions, 2 enantiomers of this. Which means in the end products, we get this enantiomer, and then the enantiomer where bromine's here and bromine's here. Right? So we get a racemic mixture, we call it. When you get a 50-50 mixture of enantiomers, that's called racemic. Right? That's a racemic mixture. So from this point, you need that. The second thing they ask you, they say, okay, you drew me the product. Now tell me if this is R, or if this is R and this is S. They want you to know that too. So you should be able to do that by now, hopefully, R and S.